Welcome in B part of lecture first. Here we will learn normalized form of a homogeneous linear differential equations and superposition principle of solutions, and then relation between nth order differential homogeneous linear differential equation with the n first order differential equations. So first, what is normalized form of homogeneous linear system? First, what is homogeneous linear differential equation? In A part, I told you I can write this is in the form of ln x is equal to 0, where x is your dependent variable and ln is your linear operator, and in the form of scalar differential equations, this ln x is written by this expression, and this is a naught t dn x by dt n plus a1 t dn minus 1 x dt n minus 1, मतलब x का आपका n minus 1th डेरिवेटिव है, and so on. dx by dt is here, and here is coefficient a n minus 1 t, and a n t operating here xt is equal to 0. This is my differential equation of nth order. आपने डिपेंडेंट वेरिएबल का n टाइम डिफरेंशिएशन किया, तो दिस इज differential equation of order n, and here is the condition a naught t is not equal to 0. ठीक है. Now I'm going to define the normalized form. On dividing this equation by a naught of t, I obtain nth derivative of x here with respect to t, and this divided by a naught, I will obtain a1 t a naught of t, and there is this term here plus a n minus 1 of t, there is a naught of t dx by dt plus a n t a naught t xt is equal to 0. When there is coefficient 1 here, this differential equation, homogeneous differential equation, is known as normalized form of homogeneous linear differential equation, and here order of this differential equation is n, so I will say this is normalized form of homogeneous linear differential equation of order n. Now I am going to define the solution. Now for the solution of non-homogeneous linear differential equation of order n, and its notation is this equation number 2, ln x is equal to f of t, and I already defined that ln x is my operator. Here a naught is not equal to 0, and all these coefficients are continuous function including f of t. These all are continuous real functions on the real interval a to b. And now we are talking about the solution. So let us take any point t0 in the interval a to b, and corresponding to this I have n arbitrary real constants, that is c0, c1, c2 up to cn. Then there exists a unique solution named as f. This is function of t of your equation number 2, such that these n conditions should be satisfied. The first condition is value of this function at t0 is equal to constant c0, and derivative values of this function at point c0 is equal to c1, and so on. Similarly, continue derivative of this function, and n minus 1th derivative at t0, this is equal to cn minus 1. And this solution, my solution is f, this defined in the entire interval, and it is a unique solution. This is my theorem, and we already prove in unit 2nd. We will use this result in this playlist to find the solutions of a system of equation also. So this theorem assures us the uniqueness of the solutions. Let us take an example of initial value problem, and my problem is d square x dt square plus 3t dx by dt plus t cube x is equal to e की power t, and initial conditions given here is value of x at 1 is equal to 2 and derivative at 1 is minus 5. If I compare this with equation number 2, here value of a naught is equal to 1. So this is normalized form of a non-homogeneous linear differential equation of order 2. Here my order is 2 here, and this is my a1t, its value is 3 of t, and a2t, this is equal to t cube, and the right hand side non-homogeneous term here, this capital F of t is e की power t. If I compare my solution x, so its value is at 1, it means my t naught is here 1 and 2 is c naught, and the value of c1 is equal to minus of 5. Okay, so all these a naught, a1, t naught is 1 and a naught, a1 and a2, all these, and including this f of t, all these are continuous functions for all for the values of t in the interval minus infinity to infinity, and this one is also belonging to my this interval, and c naught is 2 and c1 is 5. So the above theorem assure us, this theorem assure us for the unique solutions. This problem has a unique solutions in the interval in the interval minus infinity to infinity. Okay, so this is my assurance this differential equation must have a unique solution. Let us take one more example. Here the initial value problem is given by 2d cube x by dt cube plus t d square x dt square plus 3t square dx by dt minus 5x is equal to sine of t. The initial conditions, the first initial condition is x value of x at 4 is equal to 3, x dash at 4 is equal to 5, and double dash at 4 is minus 7 by 2. Now if I compare it with my standard equation 2, so a naught is equal to 2 here, this is constant, and the value of a1 it is t, a2 its value is 3t square, and a3 its value is minus 5 here, and the non-homogeneous term, that is my right hand side, it is equal to sine of t. As these are the polynomials and this is trigonometric function, so all these are continuous function for all value of x, for all value of t belonging to the interval minus infinity to infinity. The first condition of the theorem is satisfied here, and one more thing, this t naught is 4, and this 4 is also belongs to this interval where t is greater than minus infinity and less than infinity. It means my function t naught is belong to the given interval, and this constant, this is my c naught, it's my c1 and it's my c2. So the constant c naught, c1 and c2 derivative at double derivative of my solution at 4 is equal to minus 7 by 2. So by the theorem, this theorem assures us, this theorem assures us that this given problem, ठीक है, तो given problem has a unique solution, a unique solution, and this solution is defined for all value of t greater than minus infinity to infinity. ठीक है, तो हमने लर्न किया कि ln x माई डिफरेंशियल इक्वेशन है nth ऑर्डर नॉन होमोजीनियस डिफरेंशियल इक्वेशन. So there is exist a important theorem which assure us the uniqueness of the solution. Then we will study nth order homogeneous linear differential equation. It's trivial solutions, and then there is a conversion of homogeneous nth order non-homogeneous linear differential equation into system of n order differential equations. Now we have an important corollary related to this theorem. If my right hand side of the equation 2 is equal to 0, it means I have nth order homogeneous linear differential equation, that is ln x is equal to 0, and I am saying ki f is my solution of this differential equation. I can write this ln operator in this form also, so it's my standard form notations. Now if this function satisfy these n conditions, function value at t naught is equal to 0, derivative at t naught is equal to 0, and n minus 1th derivative of this function at t naught is equal to 0, where this t naught defined belongs to the interval a to b, and all these coefficients a naught, a1, an minus 1, an, all these are continuous function in this interval, and this a naught is not equal to 0. If my solution satisfy all these conditions, then we can conclude that the function is trivial. That means my solution is always trivial for this value of t in this interval. Using this theorem, I can give the answer for the solution of this homogeneous linear differential equation. This is my third order homogeneous linear differential equation. Why I am saying homogeneous? Because my right hand side is 0 and the coefficients are variable here. This is normalized form because a naught value is a naught. This is equal to 1 and this is not equal to 0. My a1 is equal to 2. My a2 is equal to 4 of t. a1 is equal to 2. a2 is equal to 4 of t. And my a3 is equal to t square, and these all are continuous functions for all value of x greater than equal to 0, for all value of t minus infinity to infinity, and this 2 is also belonging to this interval minus infinity to infinity. So by this theorem, if f is the solution of this one and satisfying all these three conditions, so I can say ki f of t, this function is equal to 0, is the solution of my this initial value problem including these conditions. So f of t equal to 0 is the trivial solutions. This is the trivial solutions. So my this homogeneous linear differential equation of order 3 has only one unique solution, and this solution is only the trivial solutions. It means my problem has only the trivial solutions with these initial conditions. Thank you so much for watching.